Here we have a digraph. As you can see here, we have arcs that connect one node to a neighbor with an associated weight, and we want to find the optimum cost path, so the minimum cost path, in order to get from O, the origin, to the target. So we want to go from the origin to the target by the shortest path, by the minimum cost path. As you can see here, we have all the weights being associated to every subpath, to every connection from one node to its neighbors. And we will do this by means of these three algorithms: the greedy, the Dijkstra, and the A-star algorithms. As you can see, we have also the heuristics for every node. And the heuristics is, as you may remember, like a rule of thumb in order to guess how big is the cost of going from the actual node to the target if you could fly. So it's the Euclidean distance. This distance is the heuristics of A. As you can see, the heuristics of A is 12 in comparison, for example, to the heuristics of C, that it's only 7, the heuristics of C, because C is closer to the target than A is. We will start with the greedy search algorithm. As you can see here, we start from O, so we mark O as an already visited node, and we check the heuristics of all the neighbors of O. As you can see, we have A, we have C, that is also a neighbor, we have F and G. All of them are neighbors. As you can see, here we have a look at the list, and A is 12, the heuristics of A is 12, the heuristics of C is 7, the heuristics of F is 10, but the smallest one is G, the heuristics of G, that it's only 5. So for the next step, we choose G. Now we forget about the previous neighbors, and we now focus on the neighbors of the actual node, that is G. G has only a single neighbor, which is T, the target, to be reached, and then obviously the target has a heuristics of 0. So we go directly to the target. Fine, so at the end, the list of waypoints of this minimum cost path according to the greedy search algorithm is O, then G, and then T, with a total cost of 10 plus 4, which is 14. Let's now use the Dijkstra search algorithm in order to get from O to T by means of the minimum cost path. Pay attention that in this method we are not using the heuristics. So as you can see here, first of all, we stay at O, at the origin, like a visited node, like an already visited node, and we check all the neighbors of the actual node, that is O. So here we have a weight of 3, a weight of 5, a weight of 10 and 4. And as you can see, the minimum is 3. So now we go to A, like the next visited node. So as you can see now, we assess the neighbors of A, which are B and D. And as you can see here, for D, the total cost is 15, because we have here a 3 and here a 12. So we add these two numbers and we have a 15. This is a 4, because we have 3 plus 1 equals to 4. And we don't forget the previous unvisited nodes, which are the neighbors of O. As you can see here, we stay with 5, 10, and 4 for the nodes C, G, and F. So now we have a tie, as you can see here. We have a tie between B and F, so we can choose either. Let's suppose that we choose F. So now we will assess all the neighbors of O, A, and F, because these three nodes are already visited nodes. As you can see here, the single neighbor of F is again G. So you can reach G by means of O to G with an associated weight of 10, but you can reach from O to G by means of F with a total cost of 4 plus 8, 12. So now, again, we check the minimum associated cost. As you can see, is B because it's 4. So now, again, all the neighbors of the already visited nodes. As you can see here, we have E, that is the new neighbor, because it's the neighbor of B, with a total cost of 8, because we have from O to A 3, from A to B 1, and from B to E 4, plus these 4. So now again we check, and you can see that the minimum cost is 5. So as you can see, the Dijkstra algorithm checks a lot of nodes. So it's optimal, but it's quite slow to run. So now the visited node is C, and we have several candidates. As you can see here, we have this new neighbor in here, this D. So now, as you can see, we have a 5 plus 6 is 11 in here. And then we also have here a 5 plus 5, it's a 10 in here. So now, as you can see, we have a tie, here a 10. But the minimum cost is not 10, is 8. So now, as the next node, as the next candidate is E. So now we compare these 10, 11, and as you can see here, we have another 10 because we can reach D by 3 different routes. O, A, D, O, C, D, and O, A, B, E, and D. So as you can see here, we now must consider this tie of 10. So the next node to be considered is G. It doesn't matter if we go directly from O or by means of C. The total cost is the same. So now we assess the neighbors. As you can see here, we have 14, 11, 15. So the next node, obviously, is here D, because we have an 11. Now you can see that we have again a tie, but whatever, if we go from O to C and then D, or O, A, B, E, and D, at the end we have an associated cost to go to the target equals to 13. So as you can see here, you have two different paths to reach to the target, and the minimum cost is this one, so by means of the D node. So you can choose with this path, so the list of waypoints will be O, A, B, E, D, and T with a total cost of 13, or O, C, D, and T with a total cost of 13. You can choose either. Maybe we will choose this because the list of waypoints is shorter than this, but this is an additional criteria. So according to the total weight, they are the same. We will now use the A* search algorithm. As you will see, this method will use both the real cost of going from one node to the neighbors and also the heuristics of this candidate, of this neighbor. Let's first of all consider all the neighbors of the starting node O from the origin. We will see that here we have a real cost of 3 of going from O to A, but the heuristics of A is 12. So we have a total cost of 15. Here for F we have 3 plus 10 because 3 is the cost of going from O to F, and 10 is the heuristics of F. Because F is closer to T than A by means of the Euclidean distance, by means of the heuristics. So we choose 12, we choose the node C as a real candidate because here we have 5, that is the cost of going from O to C, plus 7, because 7 is the heuristics of C. So now that we have C as a visited node, we consider the neighbors of C. So here we have 10, 5, and 5 is 10, plus 5 because the heuristics of G is 5. And then here we have 14 because it's the addition of 11, 5, plus 6, plus the heuristics of D, which is 3. So pay attention. When you assess the neighbors, when you assess the candidates, you must add the total real cost of getting to this candidate. So for example here 5 plus 6, and then finally add the heuristics of this candidate, so 3. So you don't use the heuristics of the intermediate nodes. So we will not use the heuristics of C when we are assessing the node D. We will consider only the heuristics of the node to be assessed. So now we have 15 here, 13 here, 15 we have a tie here, and then 14. So the minimum cost is 13. So for the next step we will assess F. So then you can reach G by means of O, of OC, and then directly from OFG. So here we have a 16, a tie, 15, and then we have a 15 and 14. As you can see, we don't forget the previously assessed nodes, like the Dijkstra method does. So now 14 is the minimum value, so the next candidate to be used as a visited node will be D. So now we add the neighbors of D. We have a single neighbor of D, which is the target, T. That's why the target has no heuristics to be added. And then we have 13 because it's 5 plus 6 plus 2, 13 plus 0 equals to 13. So as you can see here we have 15, 15, 16, and then 13. So this is the value who wins. So then, as a conclusion, we have the minimum cost path according to the A-star search method, which is O, C, D, and T, with a total cost of 13. As you can see, the shortest path by means of the A-star algorithm has been the same than the Dijkstra method, but the method is much faster. This A-star has been optimal, but by chance.